Hi guys, and welcome to what will end up being a series on cable calculations aimed primarily at level 2, but a little bit later we'll look at level 3 work as well. So I'm going to start with some definitions as you'll find them in standards BS 7671. We're looking at appendix 4. So first off we've got IB, which is going to be the design current the circuit that you're installing. Following that, we've got IN, which is going to be the nominal rating of your protective device. So whether that's a circuit breaker or a fuse, whatever, it's all given the title IN. That's followed by IZ. Now, IZ is the current carrying capacity required by your cable. So if the IZ is 6 amps, it means that your cable needs to be able to carry 6 amps. And lastly, we've got IT, which is the tabulated value that the cable can carry, and it's tabulated in BS 7671. Again, appendix 4. There's a simple rule that these have to comply with. It is IB must be less than or equal to IN, which then must be equal to or less than your value of IZ, which must then be less than or equal to the value of IT. So there's a number of steps involved There's a number of steps involved in calculating this. First we're going to start with IB. So we've got two methods of that. You can either calculate or investigate. If you investigate it, you basically just look in the manufacturer's data handbook, and quite often they will give you that information, and you just use whatever they tell you. If you're calculating it, there's a number of formulas that you can use. IB equals power divided by volts. That's for resistive loads, for instance your water heaters or your old style incandescent lamps. Second formula, IB is equal to IN. That's for your socket outlets, either a 32 amp ring or a 16 amp radial. It doesn't matter, they're still equal. IB is your power times 1.8 divided by your volts. That's for your discharge lighting, primarily your fluorescent lamps in offices and places like that. The 1.8 allows for inrush currents when it's starting up. IB equals power divided by volts times cos theta. So that's going to be your inductive loads. As you know, cos theta is your power factor, and so you're going to be looking at motors, etc. Once you've calculated IB, you go on to calculate IN. I use the term calculate because I didn't really know what else to call it, but there's no actual calculations involved. It's just a bit of an understanding about how the circuit should work, and a bit of, I hesitate to say common sense, but so you've got to remember your rule. IB must be less than or equal to IN. Okay, obviously if IN is less than IB, your circuit won't work. So for instance, if IB equals 6 amps, then IN is going to have to be 6 amps or more. Okay, there is no limit to how high you can go with IN, but it will affect the size of the cable you can install later, so keep that in mind. If you struggle to remember the different sizes of circuit breakers and fuses available, you can look in Appendix B of the on-site guide, or Table 41.2 to 41.4 of BS 7671, and all the values can be found there. Once you've calculated or chosen IN, next step is to calculate the value of IZ. So remember, that is the current carrying capacity required by the cable. Always go back to your rule, so IZ must be more than IN. Okay, so IZ is going to be equal to your IN divided by C. That C is the derating factors. IZ is how the cable is to do with how the cable is installed. So C is the derating factors due to your installation method. There are a number of them. We've got CA, that's your ambient temperature. Anything above 30 degrees ambient temperature in air will derate your cable. You've got CC, which is cables buried in the ground. Obviously you can't bury them in air, so obviously buried in the ground. CD, that's the depth of the burial. The deeper the cable, the warmer the earth. CF is your derating factor for a semi-enclosed fuse, and excuse that spelling mistake there. CG is the grouping factor, and CI, cables and thermal insulation. And lastly we've got CS, which is your thermal resistivity of soil. Okay, they can all be found in BS 7671 in Appendix 4. In particular, CA, CG, CI and CF can all be found in your on-site guide in Appendix F. For level 2 you're primarily going to use your on-site guide. Okay, so taking into consideration all of your derating factors, the formula can be rewritten as IZ equals IN divided by CA, CG, CI, CF. But effectively just ignore the factors that don't apply to you. Okay, just drop them out, they're not needed. Step 4, we're going to look in BS 7671 Appendix 4, and we're looking at table 4A2, in the on-site guide Appendix F, table F4, all the way through to F6. What we're going to be doing is we are going to be selecting our method of installation. So there are a number of methods. First of all, we've got method A. Your cables are enclosed in conduit in an insulated wall cavity. Method B, you're enclosed in a surface mounted conduit, so stuck straight onto the wall. Method C, clipped direct in free air, so clipped to a wooden beam or to a ceiling joist, etc. Method 100, your cable is contacting wooden joists in the ceiling and not more than 100 millimeters of insulation. Method 101 is the same, but you've got more than 100 millimeters of insulation above it. Method 102, clipped to a stud in a internal wall with insulation, and it can is in contact with plasterboard. And method 103, as above but not touching. Those green ones are only for flat TPS, so a twin and earth cable. Step 5, ensure your cable meets the voltage drop rules. So your power can't be more than 5% and lights can't be more than 3%. So you use the formula volt drop is equal to IB times the length of your circuit times your millivolts per amp per meter, and that is going to be divided by 1000. That formula there gives you the value of volts that you're going to drop. You then need to calculate that yourself into your percentage, and the millivolts per amp per meter is found in the on-site guide. Hopefully that makes a bit of sense, and we'll do an example in the next video so that it all sort of becomes a bit clearer. Thanks for watching.